talk before the posters. João will talk about object-centric robotics, dexterous manipulation, and causal guarantees. The floor is yours.
Okay, great. Yeah, thank you. Glad to be here. Is this audible like this or?
Yeah, shit.
Aha. So it works.
No,
Okay.
no, it is.
Maybe too much. Okay, great. Yeah, thanks. Yeah, glad to be here. Yeah, so I'm going to talk about a bunch of things here that are along the two lines of this new spectrum, I guess, which is the robotic side, the causality side, and anything in between to do with objects. So, yeah, doesn't work. Okay, it doesn't matter. Yeah. Wow. Okay. Now it's working. Great. So just a brief outline. I'm gonna do just a little bit of a unifying thread here, and then talk about the two different works. One of them is more on the side of causality, but it's mostly flavored as how we can get some theoretical guarantees that are usual in the causality side of things, but for more computer vision-y types of scenarios, which is a bit different. And then another one that's going to be more focused on robotics, very object-centric, but not necessarily causal. And I hope to make some case for how the two might be combined, and I hope that it can be done, but who knows. Okay, so yeah, so I guess we've made it this far in machine learning and deep learning along this big adventure, and seems like we made it. We've got a lot of things that work very well across the board. So now robotics should be next, right? We just need to take all of these and apply it there. Just somehow combine things, smash them together, or even just train things from scratch for robotics. Now, this is easier said than done, and there was a lot of that today in these talks. And I think one big difference here is that all of these success cases that they always required an immense data collection effort, or they enjoyed the benefits of very long simulations. So this is easier in web domains, where data is already exists, and it has some diminishing returns. But the bitter lesson so far has been that you can keep growing things. So we cannot ignore this for robotics. We cannot just pretend that we don't need big data for robotics. And there's people leading great efforts there, like the OpenX embodiment and other big data sets for robotics. But the question remains, can these ever achieve the scale of WebMind data sets? I don't think anyone could argue that even with this scale of OpenX embodiment, that we can keep riding this wave until we get to something like Instagram, 100 million, or things like what GPT was trained on. So the problem that I see is just that we don't have widely deployed consumer hardware that collects robot data in such a massive scale that we can achieve those kinds of scales. So with that in mind, it's probably we're just a little bit more bottlenecked if we care about robotics than we were in these other situations. So some possible answers might be, maybe if someone suggests more, that's great. And some could be simulation, or just better physical priors, and things along those lines. I'm going to talk about simulation later. Okay, so we're here for causal learning as well. So how can causal learning help? Well, there's one very convenient aspect of one way to do robotics and acting in the world, which is world models, especially with things like model-based RL or MPC, or planning that can make use of world models, and these could be crafted in a way by using causal learning. And another advantage of that is just make things more interpretable, easier to validate for safety, which is very important because if you deploy it in the real world, that's needed. And then also for things like exploration and to be more in a more data efficient way rather than the usual, if you know RL, epsilon greedy, not amazing. Choosing between alternative world models in a way that's a bit more like a scientist acting rather than just randomly trying things. Another way to where it can help might be just to provide guarantees for existing machine learning components. So maybe for things like in RL, knowing that your policy is going to achieve what you want, or another one would be the identifiability of some learned variables of interest. So for example, the latent variables you're learning, your model learns, are they what you think they should be? And I'm going to talk about that next, which is a good segue, I guess, because this is especially important in the unsupervised case, where you don't really know what your latents will be. So, and this is important for when you recognize that you want to, there's open set recognition when you deploy things into the real world, and you cannot just depend on or demand that all of the objects that system will encounter will be categorized. So, and so the unsupervised case is important. That's one case where you might use some of these tools from Causal. And yeah, there's probably others, but just talking about these ones. So this first work I'm going to talk about too is just being put up on arXiv. It's unsupervised object detection with theoretical guarantees. And yeah, so let's just dive into it. So it's inspired by, it uses a lot of techniques from causality, but it's more of a computer vision flavored paper. So the motivation is that when you create an object detector or an unsupervised object detector, there's always these failure modes, and you kind of expect them to happen. They have to happen because the images are messy. But on the other hand, you don't want them to happen because they are so useful. You want them for critical applications where all of these failures can be they can be pretty dramatic. So the question is, can we develop an unsupervised method that is guaranteed to detect objects? And even if the answer is no, or if the answer is yes, but we want to know what are the conditions. So when can we do it? So what are the necessary assumptions? So I guess the contributions here are supervised object detection method that is guaranteed to learn true object positions up to small shifts, and basically proving the maximum error that it can obtain in the object's positions in terms of some quantities of interest, and then synthetic and real experiments showing that this actually transfers to the real world. And you can validate this theory up to precision of individual pixels. Okay, so what we have to make things concrete enough that we can prove things. So this is one particular way to try to get unsupervised object detection going. So it's basically an autoencoder architecture. You take in an image, you pass it through a CNN, you get some map. And now the thing is, in the latent variables, you want to make sure that they can be interpreted as positions. So you sort of just you just force them to be positions. So, for example, use an operation like soft argmax to get to translate a heat map into just the coordinates of a single point, the maximum of that point. You can do this for several objects at once, and then when you want to decode it back into an image, you have to translate that back to image space, those positions back to image space, and you can do that by rendering Gaussians around those points. And once you pass that to a CNN, you can have it decode the image. It's important that the CNN is it's a CNN that is translation equivariant. So this is the reason why you can depend on, if you prove things for one part of an image, you can translate it to another. And in order to, for example, reconstruct backgrounds, you also need either positional encodings or you need to condition on another image, for example, from the same video, which I don't have here. So this is just the gist of it. It's an autoencoder. You try to reconstruct the input images, but you apply this bottleneck that is structured to look like, to encode positions of objects. And then the question is, does these actually recover images if you train it? And under which conditions does it guarantee to recover the true object's positions? So one thing to note is that there's two major sources of uncertainty here. If you think of the autoencoder, you can see there's the encoder part and the decoder part, and each of those can create uncertainty in the object position. So, for example, you might have an encoder which is the object detector, just find the very, this little tip of the object, like here, and it could plausibly still detect it. Like this is the receptive field of the encoder. Let's say it sees this little window here, and it's translation covariant, so you can see windows like this in any position of the image. So if the object is here in the red box and the encoder, the detector is here in the blue box, the furthest that it can be that it can plausibly detect an object of this given size is at this corner. And conversely, for the decoder, so you need to remember, so the autoencoder needs to regenerate the object. So the furthest that the object can be from its true position would be that it's as far away as possible, but also still inside the decoder receptive field, because you need to be able to regenerate the image of the object that includes the full object. So those are the two main sources of error we're dealing with here. And so there's this proof. This is maybe, I won't parse it. I'll just show the nice things about it visually afterwards. I'll just call attention to just one thing, which is that a big assumption is that the objects are reconstructed at the same position as the original images, which means this is a regime that you typically have in deep learning, where you have a big model, you have big data, and you expect to have zero training error. So you expect to train things such that if you don't manage to train your autoencoder to reconstruct the training images, then you probably want to adjust the architecture, you probably want to adjust things. So assuming that regime, then the question is, will it find the true positions? So we'll break this down visually, which I think is more interesting. Just give me a second. Put this here. Okay. So let's say, so there's this is a graphical representation of what was in the theorem. There's the encoder receptive field on the bottom along the horizontal axis, and it's varying. So this means as you increase the receptive field size going towards the right, you see the position error changing. So what do we see here? So there's essentially two parts to it, separated by this dashed line. The one on the left is when the error is increasing, dominated by the encoder error. So your detector is what's bounding the error of recovering the true position of the object. So initially, for the very far left, this is given. There's this error that's given for the case when your encoder is 1 by 1 pixels. So it's the smallest encoder you can possibly have. And you can imagine you have an object, whatever the size it is, but you can just segment it like pixel-wise. So if your encoder has a receptive field of size 1 pixel, this is the error that it will get for any fixed size object. And then as it gets larger and larger, the receptive field, you will get into a regime where the position error will increase linearly, because now any part of the encoder receptive field can match any part of the object. And so it keeps growing. And then there's a point where at the dash line, suddenly it just changes, and it's now bottlenecked by the decoder instead. So by your the part of the autoencoder that reconstructs the image, that's now the bottleneck. And that's where if you keep increasing the error from the encoder, it just does not influence the result at all. The difference between the two lines is that on the encoder is deterministic, so your detectors are usually deterministic. It's a deterministic function, so you expect the error to be bound by a deterministic line. But the decoder, so your image generator, in this case, it's generating an image from a Gaussian, so it's going to be probabilistic. So you get more of a probabilistic bound, which is why you see these sort of shaded lines there. And so if you train just lots and lots and lots of detectors based on this with just different random seeds and for different encoder receptive field size, you get this experimental data for some concrete values. And so you get this nice fit where the error goes up. You get a mix of all sorts of errors. But the important thing is that it gets all the way up to the theoretical bound, and it just doesn't go any further. So that's, I guess, validation from this side that you can get the points to go all the way up to the line, but not anymore. So it actually fits data relatively well. I'm going to show some more highlights of the experiments afterwards, but it's just it. Just gonna speed through the next couple of ones. That was more just a long-winded explanation. When you vary the decoder, so the reconstruction part of the network, you get the opposite situation. So initially, it's in the probabilistic regime because it's bounded by the decoder, and then eventually the other one, the encoder error, saturates and overtakes it. And interestingly, you see the same situation also in when you try to fit this to empirical data. So if you train a bunch of detectors and you see where they land in terms of position errors, you'll get this sort of fit to the theoretical line. And yeah, I think that's mostly it. One that's maybe a little bit more interesting, or what you would expect to see in when you're training an object detector would be, okay, what about object sizes? My object has different sizes. So what we observe is this sort of triangle-like shape where it's bottlenecked by different parts, again, either by the encoder or by the decoder being the bottleneck in the error. And surprisingly, the main conclusion here is that for very small or very large objects, that's when you get the smallest possible error. And very small or very large is relative to the size of the receptive fields of the object encoder that you have. So that's the kind of conclusion you can get from this one. And again, here's what happens when you try to fit this to empirical data from training lots of detectors on synthetic data. And you see that it kind of has this nice fit on the deterministic side, and then on the probabilistic side, it has just less and less probability of finding that a detector has an error that's in the low probability region of that. Okay. Yeah, there's some other one on the size of the Gaussian use. Okay, this was for some synthetic experiments where it's just rendering simple 2D objects on backgrounds, and you would do this to validate things. But also you probably want to see what happens with slightly more realistic images. So we use Clever. We haven't used Super Clever yet. I just heard about it. But yeah, what you observe in this case is that suddenly the assumption of having an object size that's always the same does not cut it for perspective images, right? Because the objects might be further away or closer, and they will have different apparent sizes. So what you need to do is extend this to consider also objects of different sizes. And when you do that, what you get is a slightly changed curve where there's an interpolating regime in the middle that's sort of bounded by the two extremes. Now, when you do this, the nice thing is that finally you can actually compare it to some baseline that you might recognize, like Samwer Cutler, different kinds of unsupervised or more or less supervised object detectors. And you can then compare them with the theoretical lines that you get from the theory. So for example, here in the encoder receptive field, so remember this is the receptive field of your object detector, you see that there's still in this Clever data set, there's still this nice fit of the red circles here, which is what the detector with this architecture gets. And you can compare that to the lines that you get, the green and yellow, which are just these two baselines. And you see that they sort of cut through across outside of what the theoretical line should give you. They're lines because they don't have a receptive field size because of the way that their architectures work. They are not just pure CNNs, so you cannot just see what they are. Yeah, similarly for a decoder, get a similar situation, maybe more interesting for the object sizes, where suddenly you can actually see what are the results for different baselines for different object sizes, and now you get a nice scatter plotted point spread of what they are. And you can see that even though on average they do work relatively well, thing is you cannot guarantee that they are going to have lower error than any amount that you want. So For the data in red, you can see that it closely follows the triangle shape of what the theoretical prediction of what the maximum error would be. While for the baselines, there's no such guarantee, so they're on average good, but also sort of all over the place because they don't offer the same guarantees. And just to drive that home, here's just, what percentage of the errors are within the bounds for any of the methods, and you can see that that's what you get. We also tested these on real data from real videos. Here you see several frames superimposed so that you can see them all at the same time and compare the fine-grained variation of the positions. But you can train on data from one source and then just generate with object positions at different positions, simulate kind of like intervention style. Yeah, so in conclusion, it's just as far as I know, the first unsupervised object detection method with guarantees, and in this case, guarantees to detect objects up to small shifts and quantifying what those shifts are in terms of the variables of interest of an architecture like this. And yeah, I think this is in a way limited, but also cool in that it's at least a way to try to get this sort of guarantee. So I'm excited to see if there's any others of this sort in the future. And here's the reference of the archive paper in case you want to check it out. Yeah, I'm going to quickly move on to the next part of the talk, which is shorter, because there isn't as much theory. It's hard to give a theory talk, but it's cool, so we got to do it. Okay, so this work is going to be presented here at the ZDPR. It's more robotics flavored. So the goal here is to do robot manipulation of arbitrary objects, but you want to go beyond just pick and place and also towards tool use and more dexterous actions. That's where we want to be at. So that rules out some sort of architectural choices that are maybe limited in how they're object-centric. We want to handle variations in task configurations and also cope with all of these errors that appear uniquely in robotics. Okay, so comparing to previous approaches of this kind, or the first ones that might come to mind, so there are some challenges. So the classic approach, which is to separate perception and control, has the problem of the main adaptation of perception. So usually the off-the-shelf detectors and all of those components that we find online, they don't transfer that well because they're not made for robotics. And also the robot models usually do not the best. Another one would be RL, reinforcement learning, but this risks breaking hardware and it's too simple and inefficient. So it's hard to apply to robotics, although there are good works pushing that direction. And another one is imitation learning. So by example, this does limit the amount of data you can get because you need to only be able to train on robots where you have humans, the examples of humans driving to robots. Okay, and then there's training and simulation. But the issues are usually that photorealistic rendering is very expensive. So, what you will see will be more like the images on the left rather than the image on the right. And it's hard to calibrate to make sure that it's accurate with respect to what the real world is like. And that goes to the sim to real gap, which if you bring up simulation, this is always the main concern, is that we do not know the parameters of the real world and it's hard to calibrate these. So yeah, so these are challenges of simulation, but it's still, you can try to push it by doing all sorts of domain adaptation, but also the easiest one that you should try is always first domain randomization. So you have to try to make it more robust by making your policy see more variations of what it will encounter, with the hope that it will make it robust to also what it will encounter when you deploy it in the real world. So here's what it looks like. This is the usual MDP-like, very robotics-focused representation of the flow. You have a simulation in the center, which is something where you can get some observations from for your robot or your policy here. So, a policy as how to act from RL jargon, sorry about that. So let's say you have your observations and maybe even goals. And from that, you just analyze that and you output an action. And based on the current state of the simulation, the robot will get a reward. That's how you train your policy using this. And the important thing about domain randomization is that the simulation is not fixed. You have different randomized parameters, like for example, masses, frictions, object, identity, object size. This is very centric on the robot arm situation, but you can generalize it. And the idea is that then the model will expect anything, which is good and bad, because then it has the problem of producing very conservative policies. So if you imagine that you learn to walk in all sorts of situations without knowing what the situation is, or if you think that the ground is shaking, then you are going to walk very slowly. And that's the kind of effect you get. You get super conservative policies that barely achieve anything. So here comes this really nice work from Berkeley. Let me just see if I can play it. Is it playing? Okay, called rapid motor adaptation. So this was mostly applied to robotics, mostly for locomotion, and it works pretty well compared to even manually engineered policies. And it was, the surprising thing about it is that this was trained completely in simulation. And you think, oh, okay, but then you adapted it somehow, right? You collected some data from the real world. Actually, no, this was deployed as is from simulation to the robot, which is, I found it very surprising when I first encountered this. So what's the trick? What's happening here? The main idea between RMA, rapid motor adaptations, is just training in two phases. So the first phase is you train a policy with domain randomization, like we saw before, but the trick is you condition the policy on privileged information of the environment. So this privileged information, things like friction masses, all of the state of your simulator that normally in the real world you would never have access to. But you cheat and you make it conditional on that privileged information. And of course, that will make it work really well. It will just learn very highly specific policies for different conditions. And this breaks the problem of learning a very conservative policy from domain randomization. It will, if it's low friction, it will deploy a policy that's for low frictions. If it's high friction, it's going to deploy a different policy. And it, a bit of training, it gets there. But then, of course, you don't want to need this privileged information when you deploy it. So the second phase is to learn to predict the privileged information from freely available observations. And this solves the problem of not having them deployed. So here's where, so policy training is a bit like the diagram we saw before, but you pass it through an encoder, and just to blitz through it, in a second phase, you just train an adapter to from an observation and action history here on the left, and in our case also a depth image, to predict the privileged information in the form of an embedding that is what the policy is conditional on. So I'm going to skip through it, but any questions about this, I can get to it. There are some aspects here that are specific to object manipulation. So it's the object-centric part. You just add learnable embeddings, kind of like codebook style, for the object identity and category. These will be privileged information, but it's treated just the same as all other kinds of privileged information from the environment or simulator. And then your environment embedding predictor, the privileged information predictor, is conditional on a depth image. So the combination of these two things makes it a proxy for object geometry, because the privileged information is what the object is, and then what you try to regress that from is from the depth image, which gets a sense of the geometry of the object. So this is a way to do object geometry while avoiding object geometry. So we tested it on a bunch of situations, from the YCB object dataset for pick and place, opening different sorts of faucets and inserting packs into holes and things like that. And these EGAB objects dataset, which has hundreds of objects that are adversarially generated. So they were generated to be hard to grasp by a genetic algorithm. The typical table where you have all the whole numbers, so it does work pretty well compared to baselines and prior work. It's pushing it a little bit compared to what some papers have done before. Here's some examples of, I'll show these in the videos, but just so you can appreciate at least what the depth images look like, this is the kind of thing. The kind of behavior you see emerging here is things like trying to insert a peg and trying to sort of, like you would do it if there's a tiny hole, like you're inserting a key and into a keyhole and you cannot see, you'll just try a bunch of different places. That's what you see here. And some other more complex behaviors on picking up very flat objects, like when you're trying to pick up a piece of paper and you're just failing and you're trying to kind of sort of turn it over a bit. So you get all of that complexity to emerge. And you would not have that complexity emerging if all you're doing is just having your policy being trained to, to first, just based on a grasp position, for example. It can be more complex and dexterous than that. So there's some examples. This is the peg insertion that I told you about. The thing you see on the top left is what the environment parameters are. So these are not just a test scenario where everything is perfect and straightforward. This is varying dramatically the parameters of the simulation, so that you can see that as you vary the object sizes, as you vary all of the physical parameters, you can still get there. Okay, so I guess in conclusion, these RMA is effective for object manipulation tasks. There's this way to get strong proxies for object geometry by treating the identity and category of objects as privileged information and then inferring it from depth. So a very sort of hands-off kind of approach to it. And this is robust extrapolation to unseen and even adversarial data sets of objects, and goes beyond pick and place into more dexterous actions. And yeah, some future directions could be multiple objects, sequencing tasks, that sort of thing. And if you are interested in that, you can check out our poster. It's on Thursday, 5 p.m. 171. And in conclusion, just trying to tie it all up, robotics has a very unique need for data efficiency, and this is very unlike other recent success cases in ML. So I think that this should give us some pause and at least trying to look for ways to deal with that, and not just assume that we're going to sit back and wait for the web data sets to grow and eventually that will solve it. I think robotics has that unique aspect. And causal learning can really help, I think. There's either just, for example, reducing the disparity between the amount of data available and how much the models need, and not just training sample efficiency, but also generalization. And we've seen some great approaches to do that in this workshop today. There's interpretability and guarantees that will become more important if you let your machine learning models act in the real world. People are going to demand it. So we can get some guarantees for these in supervised object detection, but what else is there? Can we get other guarantees for things that are, as close to applications as possible? And this model-free RL seems, like a very hands-off, still object-centric, but not very causal approach can be effective. But can we, do we need to push model-based RL more to try to integrate the things we learned from causal learning, or is there another way around it? And I would be very interested to hear your thoughts on that. And that's it. I'd just like to thank my collaborators and students, and that's it. Thanks.
Thank you so much for the nice talk. Any questions?
So I think I might have missed this, but in the second part of your talk, how are these agents evaluated? So for example, in the video you showed where their paper was having the robot walk really well, we're looking at like a qualitative thing. The video looks good, but how do they quantitatively evaluate it? Is it just reward or?
Yes. So in these, you mean for their locomotion paper? I mean for this paper for both. For theirs, I think their main evaluation metric, if I remember correctly, was the distance walked. So that's relevant for that case. In this one, the simulator we used actually, Maniskill 2 already defines criteria for success. So it's just, for example, in this peg insertion, it actually checks the coordinates of that and sees if it's all the way through or not with some threshold. We didn't define that, but definitely. So when you see success rates like the ones in this table, that's what this means. This means 73.8% of the time it can pick and place objects on these from these hundreds of categories. 62% of the time it can get the faucet to turn all the way, etc. And the adversarial object, surprisingly, that's where it gets the best 90%.
So the success rate is the metric, and that depends on the task.
Yes, exactly. That's exactly.
Any other questions? Okay, since we're a bit, sorry.
So I had a question.
Mhm.
I'll be short. I was curious. So in the second part, you assume that you have this privileged information, right?
Mhm. Yeah.
Have you thought about trying to infer it from interactions with the objects?
From interaction with the objects, yes, that's actually one of the baselines. It's the no VA baseline here. Yeah, so it's the kind of thing where it does mean that you need to, for example, touch the object and get some pushback before you can characterize it. And for some of them, that's very hard. That's even not enough with like a tiny 2 fingers gripper. Which doesn't have a touch sensor. It has to rely solely on the impact, getting into the accelerometer. Yeah, so it doesn't really cannot do that much. If we had a human hand, then we could feel our way around things. Yeah, but not with this one.
Okay.
Have you ever tested your method in real world applications?
Yeah. Yeah, we're deploying it now. I was hoping to get it ready, but robotics is hard. Hardware is difficult. It's why they call it hardware. So that's what it is. Sorry. But we managed to get it there, and just a few bugs left to learn.
Any other questions?
Which one?
Yeah, like is your success rate table, so SR with
That's the kind of like it's distance to target metric. Yeah. Yeah, and it's going to be different for each task. The units, for example, in the faucet turning, it's degrees and so on. That's why I get 180 degrees for no VA.
Yeah. All right. Well,
Okay.
thanks. Thanks again.